Okay, last example for section 8.5. This one's kind of complicated, but manageable. All right, so we have 2 sine theta equals cosine theta plus 1 for all angles between 0 and 360. So take note that we're in degrees now, not in radians. And then when we focus back on the equation, we're in terms of sines and cosines. So there's no real easy way to convert this to one trig function. We also have a sine and a cosine. So if we set this equal to 0, we're not going to be able to factor out a common trig function like we did in some of the others. This is where we have to get a little creative, similar to when you were working with the identities. So think about the identities where you had a denominator that looked similar to this, cosine theta plus 1, and we used the conjugate concept. When we used the conjugate, we created a trig function squared, which was a Pythagorean identity we could use. Now, we can't use a conjugate in this case because it's not a fraction, but we can use the concept of squaring. This is an equation, not an identity now. So we have the option to square both sides of our equation. And when we do that, we'll create a sine function squared on the left, and on the right, we'll square the entire side cosine theta plus 1, which will create another trig function squared, cosine squared. You just need to be careful when you do this, because when you're squaring both sides of this, you have to make sure you distribute both of the factors together appropriately. And then, for example, a lot of students here will just write cosine squared plus 1, but this isn't that case, right? It's a binomial times itself, so it's really cosine theta plus cosine theta. Cosine theta plus 1 times cosine theta plus 1. So we're going to square both sides. It's going to create a Pythagorean identity on both sides of the equation for us, right? So the left side of the equation, when you square it, right, remember you have to square the factor of 2, which becomes 4, and then the factor of sine theta becomes sine squared theta. And then after we distribute cosine theta plus 1 to cosine theta plus 1 and simplify, we end up with cosine squared theta plus 2 cosine theta plus 1. Now we still have cosines and sines, but because we have sine squareds and cosine squareds, we can use the Pythagorean identity to convert from sine to cosine or from cosine to sine. So game plan before you do that. The right side is made up of all cosines. The left side is made up of all sines. This cosine theta in the middle here, 2 cosine theta, there's more terms in cosine right now than there are in sine. So it's going to make the most sense to take this sine theta here, sine squared theta, and convert it into 1 minus cosine squared, right? So that's what we're going to do. We're going to use the standard Pythagorean identity, isolate sine squared theta, and then we have 1 minus cosine squared theta. So we're going to replace sine squared theta right here with 1 minus cosine squared theta. Then we'll have a trig equation in terms of all cosine terms. So doing so, I replace sine theta with 1 minus cosine theta, and now I'm going to distribute, because I know this is quadratic in nature, and when we solve a quadratic, we want to always set it equal to 0 first. So we distribute, we end up with 4 minus 4 cosine squared theta, and start setting it equal to 0 now, right? So I personally like to make my quadratic term, that's the term with the exponent of 2, positive. It just makes it easier to factor, in my opinion. So I'm going to move both terms on the left side of the equal sign to the right side of the equal sign. So I have the equation is set equal to 0 on the left. So I subtract 4 from both sides. I add 4 cosine squared to both sides. Now my equation is equal to 0. And now I have 5 cosine squared theta plus 2 cosine 1 theta is cosine to the first theta, minus 3. Again, if you're comfortable trying to factor this as is, go for it. And if you're not comfortable, then I suggest using U to help you see that factorization. So I'm going to let U equal cosine theta and replace all my cosine terms here with U. So now I have 5u squared plus 2u minus 3. Again, you can determine if this is going to factor by taking the product of the outer terms, 5 and negative 3. If you can find factors of negative 15 that add to positive 2, then this will factor. If you cannot, then you have to turn around and use the quadratic formula like we did in one of the previous examples. So factors of negative 15 are 5 and 3. It's negative 15, so one of those factors needs to be negative. So that would be a positive 5 and a negative 3. And when you add those, you get a positive 2. So this is going to factor nicely for us. And that's what we're going to do. So I turned around and just factored it. If you need to use factor by grouping and split the middle term the way I showed you last week, go for it. But the factors here become 5u minus 3 times u plus 1. And then at this stage, zero product property is up next, right? So we're going to set 5u minus 3 equal to 0, u plus 1 equals 0, and then isolate u, right? So the right term, you're going to subtract 1 from both sides. The left, you're going to add 3 and then divide by 5. And now this would be a good time to turn around and replace u back with what we originally defined it as, cosine theta. So we're going to set cosine theta equal to 3/5, cosine theta equal to -1 here. And now we're solving it just like we did in chapter 7 and chapter 8. Take note that the left equation here is positive 3/5. So that's going to be an angle in quadrants 1 and 4. And the right one is negative, but this is a special ratio for cosine, which does not put it in a quadrant. It makes it a quadrantial angle. So on the left side here, first up is to notice that 3/5 is not a special ratio. So we're going to have to use the inverse cosine of both sides. And so when I take the inverse cosine of both sides, theta ends up becoming 53.13 degrees. Again, make sure you're set in the proper units in your calculator before you take the inverse cosine. So we're working in degrees, and calculator's going to spit out degrees. 53 degrees is an acute angle, which means it's a reference angle at the same time, which is very helpful. And I'm going to turn around and sketch angles in quadrants 1 and 4. So my blue quadrant 1 angles right here, red angles, red reference angles right here, they're the same. So we have one solution already, 53.13 degrees. Fourth quadrant angle with the same reference angle as quadrant 1, 53.13 degrees. So I want to find this green angle here from standard position. Remember, full rotation is 360 degrees. So I need to subtract this red reference angle here from 360. It's going to give me 306.87 degrees. That is my fourth quadrant angle. So for this, this equation alone, I have two angle solutions, 53.13 degrees and 306.87 degrees. And next up, I'm going to start working on the other equation. Okay, so remember, cosine theta equals -1 is produces a quadrantial angle. -1 is a unique ratio for us. So it's best to view this on the unit circle. Remember, cosine theta really is the ratio x over r. And when we're working on the unit circle, r is 1. So really what we're just looking for is what points around the unit circle, or what angles around the unit circle produce intersection points where the x coordinate is -1. There's really only one. It's at 180 degrees right here in green. So we have one angle solution in this situation of 180 degrees. And then now that we've identified the three angle solutions, we can turn around and write them in a solution set here. Least to greatest, 53.13 degrees, 180 degrees, 306.87 degrees. And this satisfies this equation now.